Hi, this is Calculus 12, Chapter 3.4. We're going to be looking at velocity and other rates of change. Recall this is the formula for the tangent or slope. And because it's the tangent or slope, the derivative is the instantaneous rate of change. So we have slope equals displacement over time. So we would have meters per second, and this is velocity. And this is for a displacement time graph. So if we have a velocity time graph, and we do the slope again, this is the second derivative. So we have velocity over time. That's meters per second. So this is meters per second squared. And this is acceleration. So this gives us the following. Displacement would be our f of t. Sometimes this is called s of t. Our distance is actually the absolute value of f of t. Note that this is a vector. This is a magnitude. So a vector has direction, a magnitude does not have direction. Velocity, we can say it's v of t, or we can say it's the derivative of f of t. Again, this will be a vector. Speed is the absolute value of the velocity. And again, this is magnitude. Acceleration, we use a of t as the function. Or we can use v prime, or we can use f double prime. And again, we can use s here as well. And here's one that you probably haven't heard of. The change of acceleration is called the jerk. So we have a prime of t, or v double prime of t, or f triple prime of t. If you're going to use Leibniz notation, this is d squared f over dt squared. This is d cubed f over dt cubed. So you have to put it in this order. That's just the notation. Let's look at an example. A drag car's displacement in feet is given by the formula f of t, 51t squared minus 2.5t cubed. So these are the questions that we're going to be answering. Find the velocity and acceleration as a function of time. Find the velocity after 6 seconds in miles per hour. When does the dragster reach maximum velocity? Find the maximum velocity in miles per hour. Note that 5280 feet is 1 mile, and 1 hour is 3600 seconds. That's 60 times 60. 60 minutes per hour and 60 seconds per minute. So v of t, all we have to do is take the derivative of f of t. So we have 51 times 2 times t minus 2.5 times 3t squared. So we get 102 t minus 7.5 t squared. This is in feet per second. We'll have to convert it to miles per hour later. Acceleration, we'll just take the derivative of velocity. We'll use the last calculation here. So it's 102 minus 7.5 times 2t. And we can simplify that to 102 minus 15t. This is going to be in feet per second squared. So we've done this, check. Now we have to do this, find the velocity after 6 seconds. So it's just v of 6. We just plug 6 into here. So we have 102 times 6 minus 7.5 times 6 squared, that's 36. That gives us 612 minus 270. That gives us 342 feet per second. We need to multiply this by 3,600 seconds per hour over 5,280 feet per mile. So the seconds will cancel out, the feet will cancel out, the miles is in the denominator of the denominator, so we can flip that into the numerator. That gives us 233 miles per hour. Okay, when we have mh, it wouldn't be meters per hour, so you have to understand from the context it's miles per hour. A of t, so that's done. When does it reach maximum velocity? That means the acceleration must be 0. So we're looking for 0, and we just plug in the function, 102 minus 15t. That means 15t equals 102. So t equals approximately, we'll do approximate, and we'll give a decimal answer, 6.8 seconds. So that's done. And find the maximum velocity. So now we need to do v of 6.8. It's probably better to do v of 102 divided by 15. That will eliminate the rounding errors. We'll bring up a calculator. We have 102 times 102 over 15 minus 7.5 times 102 divided by 15 squared. Be careful about where you put the brackets and where you square it. This gives us 346.8 feet per second. And now we have to convert that. So we're going to multiply by 3,600 over 5,280. And we get 236 miles per hour. Let's look at another problem, tree growth. So if you cut a tree trunk, do you see this or do you see this? You see this. Our change in R is going down with each ring. So each ring gets a smaller increase in radius. Here, the increase in radius is constant. That means our area is going up. If we decrease the radius as we're going out, the area of the ring is going to be approximately constant. And tree growth is dependent on sunlight. So the amount of sunlight is pretty much constant after a tree grows a certain size. Because it's constant, it can only grow at a fixed volume. Okay, and this would mean the volume's increasing as it's growing. Calculus can be used in economics, and we can look at these formulas when we're doing mass production. And it doesn't make sense on a small scale because what happens is we produce integer or whole numbers of units. We don't normally produce fractions of units in mass production. So we don't manufacture part of a car We don't manufacture part of a TV. We manufacture whole cars and whole TVs. Okay, so if we have C is the cost to produce X units, and we have R as the revenue from selling X units, whenever we take the derivative of a cost or revenue, that's called marginal. So marginal cost is going to be C prime. Marginal revenue is going to be R prime. Okay, so if we have blue as our cost, red as our revenue, this is a loss. So if we're doing revenue minus cost, we're losing money because it's costing more to produce than what we make. Here, revenue is higher than cost, so this is profit. So P of X equals Rx minus Cx. Okay, and marginal profit is going to be the derivative. And we maximize marginal profit when P double prime of X equals 0. So you can look at it as taking the derivative of the marginal profit or just the second derivative of profit. So anytime a question asks for a change of quantity, we want to take the derivative. And marginal means change. And change means derivative. We're doing calculus, so take the derivative if you're unsure. Marginal cost. So we're looking at the dollar cost of producing X washing machines is CX equals 2,000 plus 100X minus 0.1X squared. Find the average cost of producing 100 machines. Find the marginal cost when 100 machines are produced. Show that the marginal cost of 100 washing machines are produced is approximately the cost of producing one more machine after the first 100 have been made by calculating the latter cost directly. Okay, so you have to practice these to get used to how the wording is. And whenever we're doing the average cost from the start, we have to do CX over X, not CX minus C0 all divided by X. This will ignore the starting cost of producing the machines, which is this constant value here. So this constant value must be taken into account into the average cost if you're going from the beginning. So A, we're doing this. C100 over 100 equals 2,000 plus 100 times 100 minus 0.1 times 100 squared, all over 100. Plug that into your calculator, and you get 11,000 over 100. So that's $110. Don't forget your units. B, find the marginal cost when 100 machines are produced. So we need the derivative. C prime of X equals, that's a constant, that goes to 0. This is a 100, and we use the power rule, so this is 0.1 times 2x. We can simplify this, 100 minus 0.2x. C prime of 100 equals 100 minus 0.2 times 100. That's 100 minus 20, so that's 80. Okay, here's where the wording is the most tricky. What is the cost of producing one more washing machine after the first 100 have been made? We need to do C101 minus C100. And technically we're doing 100 and 1 minus 100. That's just going to be 1. We've already calculated this, so we don't have to calculate it again. So 2,000 plus 100 times 101 minus 0.1 times 101 squared minus 11,000. This equals 11,079.9 minus 11,000. So that's 79.9. That is roughly 80. So yes, they are approximately the same. Let's look at the next problem. We have to be careful here. It says the position, the x-coordinate of a particle moving along the line y equals 2. That's important, is y equals 2. Given by x of t equals 2t cubed minus 13t squared plus 22t minus 5, where t is the time in seconds. Describe the motion of the particle. So before we start, if you plot this, it's going to look like this. However, this is what it's going to look like in time, but it's actually going to be moving along y equals 2 back and forth. So it's moving back and forth along here. Let me erase that. Okay, so we need to describe the motion. Here is where it changes direction. If we're looking at the function plotted this way, we're looking at the maximum and minimums. Okay, so it's changing direction at the maximums and minimums. So it's moving right here, it's moving left here, and it's moving right here. It's easier to see here. We're moving right, we're moving left because it's going this way, and then it's moving right again. This is x and t, and this is reverse. This is x and t. Your calculator won't be able to plot this because this is a relation. This is a function. So you have to do an inverse plot. Okay, so you just swap the x and y values. Next, that's done. When does the particle speed up and slow down? Let's calculate the velocity, which is the derivative of this. So v of t equals 3t squared minus 13, 2t plus 22. Okay, we can just plot this. It's not asking for us to do this algebraically at this point. This is v and t. So here's where it's slowing down as it's going towards the x-axis, because the x-axis is 0 velocity. It slows, and then I'm going to do speeding up in a different color. So it's speeding up all the way to here. Speeds up. This is moving away from the x-axis, so this is speeding up. This is slows. And this is slowing too, because it's moving towards the x-axis. Okay, so the note here. Okay, so we should answer this with a little bit more detail. So you would find the zeros here, and from 0 to 1.15 seconds, slows from 1.15 seconds speeds up. So you would find the zeros here and here. Here you would have to find the minimum to get this value. Okay, so this is 1.15, this is 2.17, this is 3.18. Notice that I didn't put any equal signs in here because it's not speeding up or slowing down at this point. It's zero. Here, it's going from speeding up to slowing down, so we wouldn't put an equal sign there. Next, when does the particle change direction? So that means we're changing directions from left to right. We looked at this earlier. It's at this point, so the maximum and minimum of our f function. Okay, so at this point, so we want v of t equal to 0. So we have 6t squared minus 26t plus 22 equals 0. This actually doesn't factor. We can reduce it. 3t squared minus 13t plus 11 equals 0. So it changes direction at 1.15 seconds and 3.18 seconds. D, when is the particle at rest? Okay, so when it's changing directions, it's actually at rest. It's just stopped just for an instant when it changes directions. So we have t is approximately 1.15 seconds and approximately 3.18 seconds. E, describe the velocity and the speed of the particle. Okay, so we already have v of t. That's 6t squared minus 26t plus 22. The speed is the absolute value of v of t. So that's just the absolute value of 6t squared minus 26t plus 22. Okay, so describe the velocity. We'll do that first. That's over here. So we'll do round brackets. 1.15. That leaves out the equal sign. It's positive and slows. Actually, this can be included. 1.15, 2.17, negative and accelerates. And 2.17 to 3.18, negative and slows. And 3.18 to infinity. Infinity should always have a round bracket, positive, and accelerates. Okay, let's look at the speed. So when we're answering speed, there's no direction. So it's the same thing as here, slows, accelerates, slows, accelerates. And the last question. When is the particle at the point 5, 2? It's always on 2, okay, because it's moving horizontally. So all we have to do is figure out when it equals 5 for F or X. We only have to figure out when X equals 5. So X of t equals 5. And because that's not going to factor, we're just going to solve it on the calculator. So t equals 0.74 seconds, 1.63 seconds, and 4.13 seconds. And that completes this lesson.